What is a standard deviation? Imagine that we have taken a sample and the sample is normally distributed, and in here we do have the sample mean in the middle here. It's a sample, so we don't know what the actual population mean is. So we want to make an interval around the sample mean in here. So we have an interval in which we think the actual population mean will be. We would like to be 95% sure, so we create a 95% interval, which means that we are right in 1 out of 20 times. So first of all, we have to go 1.96 standard deviations to this side, and we have to go 1.96 standard deviations to this side. But where does this 1.96 come from? First of all, we do have the normal distribution, which is centered around the mean with a variance. If we take the formula for this curve here, it looks like this. It's 1 over 2 pi sigma squared, variance squared, times e to the minus over 2 sigma squared, x minus the average squared dx. Then we do have the integral of it, which is the area in here. Now we would like to have 2.5% because we cut off 2.5% here and cut off 2.5% here. Then we do have 95% in here. But where should we go from here? Imagine this is back in the 18th century and nobody can actually do this calculation. It's pretty hard to do, but along comes this guy, Gauss. And that is why this is called the Gauss distribution. He says, hey, wait a second, what happens if we deduct the mean from the standard, from the actual random variable? How's it then distributed? It is, of course, distributed around 0, because if you take the sample mean and deduct it from the sample, it will be centered around 0. So that's what Gauss did. And then he divided by the variance, because by dividing by the variance, we suddenly get a variance of 1. So 0 divided by sigma squared is 0 still. Sigma squared divided by sigma squared is 1. And because it's in here, it's squared. Out here, it's just normal sigma. So it's our random variable minus the mean divided by sigma. That's how he came up with. And then he said, let's see, what does this look like? Then suddenly we do have a different integral here. It's because sigma is 1, that is just 2 pi in here. We can put it outside, doesn't really matter. It's just a number. And here and here we have e, sigma squared again is 1, so it's minus a half. Mu is 0, so it's x squared dx. So basically we want this to be 0.25, and then we only have to go up to minus 1.96. That's what he came up with, and this is where you get this beautiful table from. If we go in here at 1.9, up here at 6, in here we see 0.975. 0.975, what is 0.975? Yeah, that is the area from this here and downwards. That's 0.975 because it's the positive side, 1.96. If we in here had taken minus 1.96, it would have been 0.025. It's the 2.5% on each side. So now we do have that this must be bigger than minus 1.96 and less than 1.96. Then we just go backwards. We multiply by the standard deviation on both sides. So suddenly we do have it. It's centered around 0, but no longer but now with a variance. And we do have minus 1.96 times the standard deviation and 1.96 times the standard deviation. And we're going to add the mean on both sides. So it's the mean minus 1.96 and the mean plus 1.96. And in here we have our random variable, which is distributed with a mean and variance, which is where we came from. And this is where the 1.96 comes from.